let's talk about derivative rules. So we're going to kind of start at the foundation here, quickly go over what we've already learned in regards to working with derivatives, and then begin to extend that to some rules that are going to make our life a little bit easier. So fundamentally, do we remember the derivative of a function? Yes, it is what we use to solve the tangent problem using differential calculus. So we have some curve f of x, or some function f of x. And if we're considering it visually, the derivative is what we're using to find the slope of the tangent at a given point. And that's what we see here. And that's what we've been seeing for the last little while. So tangent line touches the curve at only one point, and at that given point, we have that linear line, and the slope of that line is the value we get from our derivative. And in terms of notation, we might write it something like this, f prime of x, or something like this. The derivative of a function, f of x, is actually a new function, f prime of x, which represents the slope of the tangent. So remember, it's giving the slope, not the whole line of the tangent right away, or the instantaneous rate of change at any point on the curve of f of x. The derivative function is defined by the first principles definition for the derivative, f prime of x equals limit as h approaches 0 of f of x plus h minus f of x over h. And if we were to sketch a curve, the basic idea is that we are looking at our point f of x plus h and our point f of x, and this point is x, and this point is x plus h, and so the gap between them, the change in x values, is our h value, and we're letting h, the value of h, get vanishingly small, so we're moving this line closer and closer. So that's what it looks like visually. If the limit exists and the slope of the tangent is equal to the limit as h approaches 0 of the secant. So we're taking our two dots and bringing them so close together that they are basically in the same location. And we've also talked about different notation for the derivative of f of x. So it might be written as f prime of x, dy dx, ddx of f of x, or even simply y prime. And let's also remember that if a derivative does not exist at a point on the curve, the function is non-differentiable at that x value. So just by definition, can't find the derivative means non-differentiable. This can occur at points of discontinuity. So if there is an asymptote, or a hole, or a jump discontinuity, or where the function has an abrupt change indicated by a corner or a cusp on the graph, or where the tangent to the graph is vertical, and thus the slope is undefined, those are the places where the derivative does not exist. And we've seen those all before, just good to reflect and review on what we know. So this brings us to our limit definition, first principles of a derivative. Dy dx equals limit as h approaches 0 of f of x plus h minus f of x over h. So this is super important and helpful. It lets us solve a challenging problem of finding the slope of a tangent at a given point, but it's not very fun. It's super important, but slightly exhausting. So far we have actually seen a few shortcuts that will make our life a little easier, or have made our life a little easier already for solving these kinds of problems. We have worked with exponential functions. We have seen that the derivative of e to the power of x is itself e to the x. We've seen that the derivative of some constant k times e to the x is equal to k times e to the x, so the constant doesn't change. And we've seen for any other value for my base, so derivative of any number b to the power of x, except when b equals e, Well, actually, I guess it's still true. It just simplifies. We're going to get ln b times b to the power of x. So the same thing stays there. We have our original function, and we're multiplying by a constant, and that constant value is ln of b. Let's a couple examples real quick. We might see things like this. Y equals 2 e to the x. So the derivative, y prime, well, that's just equals 2 e to the x. Convenient. Or if I have something like y equals 3 to the power of x, it's going to simplify to ln 3 times 3 to the power of x. Oops, y prime. There we go. We also have some shortcuts for working with trigonometric functions. You've seen that the derivative of sine x is equal to cos x, and the derivative of cos x is equal to negative sine x. And we will note briefly that x must be in radians. All right, we are now ready for some more shortcuts. So let's take a look. Let's learn a few more tricks and tips that will make our life a little bit easier. First up is the constant rule, and we're just going to look at constant functions. So first, what is a constant function? Constant function is a function that just has the same value everywhere. So as an example, we can take a look at y is equal to 3. Actually, I guess I'll look at the example they have here in the note. So in this case, let's example the graph of f of x equals 4 to make predictions about the derivative. So we have our x and y axis, and we have a horizontal line with a slope of 0 just running along our graph at y is equal to 4. So we can locate points on our graph. A is 3, 4. We could have another point 4, 4, or 6, 4. Wherever we go, we can choose any value for x we want. There's no restrictions, so x is an element of the real, but y always has a value of 4. So let's think right away. What do we know about the slope of this line? What do we know about the derivative of this line? Well, it's going to be 0 everywhere. And if I had another line, another constant line, such as f of x equals 3, same thing's going to happen. F prime of x is just a horizontal line with the same y value everywhere, so the derivative would be equal to 0. If we were to draw a tangent to this function at the point a of 3, 4, the tangent line would be horizontal, and we can sketch that right away, and have a slope of 0. This would be true of any function. This would be true of a tangent to any point on f of x. This would also be true for any other constant function. So by this brief investigation, we may predict that the derivative of any constant function will be 0. So as soon as I see a function that's just y equals some number, I know that the derivative is going to be 0. To prove that this statement is correct, we will use the first principle. So we're going to prove the constant rule. Let f of x equal c, where c is some constant real number. And using first principles, find a general equation for differentiating constant functions. So we start with our first principles definition. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. And what's our value for f of x plus h? Actually, let's start with our f of x. So at f of x, we're going to have some constant value. If we move over a little bit on the graph, f of x plus h, we're going to have some constant value, the same constant value. So let's think about that for a moment. So this is my original point, x, and f of x, and I'm moving over to my point x plus h. Well, I'm going to have the exact same value. They're going to be the same. So it's just the c value, the constant value times itself. So f of x plus h and f of x have the exact same value. Any number minus itself is 0. Or, yeah, that's fine. And so this is going to simplify and just be 0. So the value of the slope of the tangent in this case is 0. Therefore, when f of x is equal to c, where c is any constant and c is an element of the real, the derivative is equal to 0. Let's work through a few examples. I would encourage you to pause the video here and try working through these on your own for a moment. When you're ready, resume and double check your answers. For A, we're looking at f of x equals -2. So our c value is -2. And so what's our derivative going to be? Well, it's going to be 0. And we could sketch that really quick as well. Although it's pretty simple, we can probably just visualize that in our head, no problem. Yep, that's a horizontal line. Definitely has a slope of 0. In our next case, f of x equals pi. So it doesn't matter that it's not an integer. Pi is fine, so my c value is pi. My derivative, well, it said it's constant, so it's going to be 0. And let's just visualize that quickly once again. X and y, 1, 2, 3, 4. So pi is going to be around here. So I got my nice horizontal line running through. Yep, that has a slope of 0 everywhere. So it makes sense that the derivative is equal to 0. And finally, f of x equals 5e squared. Well, remember, e is just a number, and 5 is just a number. So this is just going to have the same value everywhere. So this is still a constant value. So it's just like, imagine we were looking at 5 times 3 squared, which would be a similar looking graph. That's just going to be the same number all the time. And remember, e is just a number, so this will also just be a number, just have a constant value. So our derivative is going to equal 0, and if we were to sketch it really quick, x and y, 1, 2, 3. My value for e is in between. And so a horizontal line through y equals e, or 5e squared, or whatever our value is for our function here. And that's just going to be flat line, horizontal everywhere. The derivative of 0 everywhere. Great. Next up, we have the power rule for power functions, and this is where we really start to save some time working with our derivatives and having a really useful tool in our toolbox. Some of you have already noticed a certain pattern. If f prime of x equals x cubed, if f of x equals x cubed, then f prime of x equals 3x squared. And this is related to those ideas we looked at earlier, where I saw that if I had a linear function, then the derivative was a constant value. And if I had a quadratic function, then my derivative was a linear function. And if my function was cubic, then its derivative was quadratic. And if my function was quartic, then its derivative was cubic. And so we're going down 1 degree in our equation. So if it had a power of 3, its derivative has a power of 2. If it had a power of 2, the derivative is linear with a power of 1, and so on. And now we're just making this a little more specific instead of just describing the degree of the function in general terms. So let's start with the rule, and then some examples, and then look at the more complicated proof of the rule. So first, what is a power function? Well, it's just going to be anything with a degree on the variable. So we're going to have something like y equals x, so that, equals x to the power of 1, y equals x squared, y equals x cubed, y equals x to the power of 4, and so on. And of course, these are just our parent functions. I might have extra transformations added. I might have like x squared minus 3x plus 2, things like that. But let's see what our power rule actually states. It says that if f of x equals x to the power of r, for r is an element of the real, then, and here comes the good part, f prime x equals r times x to the power of r minus 1. So basically, let's say we have x to the power of 4. We're taking our number, we're moving it down in front, and we are subtracting 1 from our exponent, or our power. So 4 minus 1 becomes 3. In Leibniz notation, it's going to look like this. Doesn't change the meaning, just different notation. d dx of x to the power of r is equal to r times x to the power of r minus 1. We have a few examples here. Let's determine the derivative for the following functions. Once again, I encourage you to pause and then try these on your own before continuing, or you can watch the first one and then pause and then figure it out on your own. And I don't really have enough room on this page, so I'm going to jump to my Notes app and work through this there, so there's enough room to actually show our work. All right, let's go ahead and find the derivative of these power functions. First one's pretty simple. F of x equals x to the power of 5. And we need to find the derivative. And so we've seen from our power rule that we're going to bring our exponent down to the front. It becomes our constant. The variable stays there. And I subtract 1 from the original value of the exponent. And so we're going to get f prime of x is equal to 5 times x to the power of 4. And isn't that nice? That's so much faster than having to use the limit definition and needing several lines of calculations and expanding and simplifying and substituting in a. We can just take this shortcut. So it's really important that we are familiar with the limit definition and able to work with it and understand where that stuff comes from. But now that we have a handle on that foundational knowledge, we can start to take this shortcut to make our life a lot easier. Next up, this one looks a little different. I have an exponent of -1, but that's not a problem. We're just going to follow the rule just the same. F prime x equals, bring that exponent down in front as the constant value, times x, and we just subtract another 1 from the exponent. So we're going to have f prime of x is equal to -1x, or just negative x to the power of -2. And depending on how our question is phrased, we can rewrite this as -1 over x squared. So remember, anytime there's a negative on in our exponent, that means if we can rewrite it as the reciprocal. So it's kind of like when we have anything to the power of -1, we can bring it down. If there's a value on it, or a non-1 value, actually it doesn't matter because there's a 1 there as well. That comes down as well. So we kind of like use the negative up, bringing the number down, or we can think about that negative being transformed into our division symbol here, if that's a helpful way for you to think about it. And then the 2 gets carried down as well. In our third example, f of x equals the square root of x. And you're like, Mr. Strike, that's a square root. There's no exponent on there. Well, I hope you also remember that what we can do is rewrite this f of x is equal to x to the power of half. And that power of half represents our square root. So this looks a little more like a power function now. Let's go ahead and use our power rule to differentiate. F prime x equals, let's bring that exponent to the front as a constant. My variable is unchanged, and my exponent's going to be half minus 1. So I can rewrite this as f prime x equals half x, and half minus 1 is -1/2. So f prime of x is equal to, we'll bring this down, 1 over 2 x to the power of half. So the negative gets used up, so to speak, bringing the number to the bottom. And f prime of x is equal to 1 over 2 root x. And of course, if we wanted to rationalize our denominator, we could, but that's not the focus of this question right now, so we're not going to worry about that. And finally, once again, you've probably seen the connection, but the number's on the bottom, so how, like, this is a power function, but it's in the denominator. How does that affect things? Well, let's just rewrite our original equation first. F of x equals x to the -2. Now let's apply our power rule. F prime of x equals, bring that exponent down out front. The variable remains there. And to the power of -2 minus 1. And so I'm going to have f prime of x is equal to -2x to the power of -3. And once again, depending how the question is phrased, how they want us to represent our final answer, we could rewrite this as -2 over x cubed. All right, that wasn't too bad. Continuing on, how can we prove the power rule? Obviously, we need to go back to first principles, but first let's review some factoring. So in the first case, if I have a difference of squares, so my first term and my second term are both something squared, and difference, so we're subtracting. We're going to have the difference of the original values, a minus b, and that's going to occur every time for in our pattern here. But then our second part here, we're going to note specifically that there are two terms here. So difference of squares, a squared minus b squared is equal to a minus b times a plus b. So this is our difference of squares. Next up, we have our difference of cubes. We're going to have the same starting term here, but then our second term, or our second expression, or our second factor here, a squared plus ab plus b squared, has three terms. And if we have, so this was our difference of cubes, and if we have a difference of fourth powers, a to the power of 4 minus b to the power of 4, we're going to have that original term there again, a minus b times a cubed plus a squared b plus ab squared plus b cubed. I'm just going to have four terms, and so on. So there's a pattern there that we want to observe here, that the number of terms here is equal to the number of terms here. So we've worked through several examples now, but the question remains, how can we prove the power rule? Obviously, we need to go back to first principles. First, let's review some factoring. If I were to have a difference of squares, a squared minus b squared, the factors are going to be a minus b, and that's going to be our factor that we see in each of these cases here, times a plus b. And we notice this has two terms. With a cubed minus b cubed, so a difference of cubes, we're going to have a minus b as our first factor, times a squared plus ab plus b squared, and we notice that there are three terms in that factor. And if I look at a difference of fourth powers, a to the power of 4 minus b to the power of 4, my first factor is once again a minus b times a cubed plus a squared b plus a b squared plus b cubed. And there's a difference of fourth powers. So we notice four terms, that our number of terms is equal to the degree of our items we're taking the difference of. If we were to extend this to the nth degree, so extending this to as many values as we need to, or in other words, writing a general formula for this, a to the power of n minus b to the power of n is equal to a times b, there's our friend again, times a to the n minus 1 plus a to the n minus 2 times b plus a to the n minus 3 b squared plus a to the n minus 4 times b cubed plus, and so on until we get to just a by itself times b to the power of n minus 2, and then plus b to the n minus 1. And this is our difference of nth powers. And we notice that how many terms are in my second factor? There are going to be n terms. Now we are ready to prove the power rule if n is a positive integer. And honestly, you can use the power rule without working through this slide, without understanding where the rule comes from. In terms of foundational knowledge and having a true understanding of what's happening, it is a good idea to work through and understand where do my formulas come from, why do they work. But if you're confused by this part, don't worry about it too much. It is possible to still continue and still apply the power rule without having a full grasp of where it comes from. But let's take a look. Let's try to prove the power rule if n is a positive integer, as long as we remember what we just observed about factoring when we have a difference of terms to the power of some value n. So if f of x equals x to the power of n, then by first principles, we know that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And in our case, we're looking at x to the power of n as our f of x. So the limit as h approaches 0 of x plus h to the power of n minus x to the n over h. What is this going to equal? Well, we just talked about a difference of squares here. And so my difference of squares is the x plus h to the power of n. So that's like my a value minus my b value, which is x. So let's observe. We're going to use our piece here and write it out here. So that represents our difference of squares. So our a minus b value is here, and then our second factor is here. And I don't want to read all this through, but basically we are taking this piece right here and mapping it onto this piece here. We're replacing our a and b value with our, yeah, that's right, with our a and our b value from here. And we go through and simplify. We see we can factor out an h, so the h's are going to cancel. I'm just going to be left with this part right here. We're going to take the limit, so all my h's become zeros, and we're familiar with this. And as we go through and simplify and rewrite using our exponent laws, so x to the n minus 1 and x to the n minus 2 times x and x to the n minus 3 times x squared. So we notice that we're kind of canceling out some of the x's here. There's another x here, so that's a 1. There's 2 x's here, so this is a 1. There's 3 x's, there's 1 x here, 1, and so on. This is going to simplify nicely, and it's going to give us just the same thing times itself multiple times, x to the n minus 1. And how many terms are there in that bracket? Well, we already said there are n terms, so it's going to be n number of terms times x to the power of n minus 1 as expected. So I didn't read through everything there. I'm not going to be super rigorous. The details are here if you want to work through, but like I said, to be honest, while foundational knowledge is important, as long as we understand that we can prove it, it is not necessary to prove it. I'm not going to ask you to do that on a test or anything. Let's summarize what we've learned so far with our derivative rules. So summary of derivative rules so far, we have learned the constant function rule, and so I might apply this to a function like f of x equals 3. If f of x equals some constant value c, where the constant c is an element of the real, then the derivative f prime of x is equal to 0. And in my Leibniz notation, for some constant c is an element of the real, d dx of c is equal to 0. We've also taken a look at our power rule, and we might apply this to a specific example like f of x equals x to the power of 8. So if f of x equals x to the power of r, where r is some real number, then f prime of x equals r times x to the power of r minus 1. So my derivative in my specific example here is going to be bring down that number 8, x, and subtract 1 from the exponent. Looks pretty good. And in our Leibniz notation, d dx of x to the power of r equals r times x to the power of r minus 1.